Hello, hello, hello. Good morning, good afternoon, good evening. You have reached Saturday Science Chats. Hey, thanks for tuning in to Saturday Science Chats. I'm Dave D. Hilster, and I want to welcome everybody from the John Chappell Natural Philosophy Society and the Dissident Science channel. Today we have a great show today. You don't want to miss it. We're going to talk about the possible physicality for electronic circuits. And with my father, Robert D. Hilster. So it should be a lot of fun. Yep, that it is today. The particle model, electronic circuits with Robert D. Hilster. There he is in his lab, in his room, in his suite in our house here. And that is his lab setup. Believe it or not, that looks like not a lot, but there's quite a lot of expensive equipment on that little card table. And also the experiment itself probably costs only a couple dollars or whatever. But anyways, it's going to be an absolutely great talk. He's got some two experiments going to talk about how that were being supported or supports the particle model. That is, the particle model predicted a couple of things, and he actually has measured them. He's going to talk about that today. But of course, I want to congratulate you. Congrats for watching this channel. It's very important for your support because people who watch this channel are people like Aristotle said over 2,000 years ago. It is the mark of an educated mind to be able to entertain a thought without accepting it. That means you come here to find out new ideas, new views of the universe, because we know I'm going to be giving a talk actually a couple weeks from now, and in that talk is going to be the majority is always wrong, because that's where people get stuck in their ways. So if you've come here, you're not in the majority. You want to be people who are critical thinkers going forward, like my t-shirt says. And I also want to thank so much my subscribers. We passed 4,000 subscribers a couple weeks ago. I want to thank all my subscribers. And I do want to thank everybody who watched our video from last week. Actually, we broke all records with that video. Normally, it takes months, if not years, for us to get over 1,000 views for one of our videos here. But we got over 1,300 views in like about 4 or 5 days of our video from last week. So thank you so much for tuning in and watching our presentation on the particle model. We got a lot of great things coming up this year, so you don't want to miss them. And again, if you want to come to the green room, you can live. I'll tell you how you can do that. But our mission, of course, is to be an organization that above all promotes critical thinking without malice. That is, if you have a better model for the universe, we're not going to tell you, oh, it's not accepted by a mainstream, so you can't do it. No, we support that. Our organization supports, publishes, promotes serious scientific work outside the mainstream. We provide a forum for open debate in physics, cosmology, philosophy, mathematics, and other areas, and we provide a forum for serious papers and theories without fear of censorship, and we are run entirely by our members. Also, we do have websites, so if you are really new to this is the first time you've stumbled upon our live here Saturday Science Chats, take a look at beyondmainstream.org. It's an online magazine for critical thinkers, written in more of a magazine kind of way. Amazing articles, really well. You're going to find all kinds of people you probably never heard of doing an amazing work outside of the mainstream. People have PhDs from MIT, all the way to a ex-Supreme Court justice who is actually working in the area of science after retirement. And we have all the ways you can see, click on there and find all the problems in mainstream science. You want to check that out. It is a really great, I think we're coming up over almost 100,000 views on that. And then naturalphilosophy.org, if you want to join in the conversation with other critical thinkers around the world, you can go to naturalphilosophy.org and sign up and register. And also, we do have a Wikipedia of information. It is a true wiki that uses the same software as Wikipedia, but you can go to wiki.naturalphilosophy.org. We have over 10,000 pages of people, again, working outside the mainstream, serious critical work. Where we believe in the scientific method. So, and we are supported by our members, and we do appreciate your membership. I know we have monthly members. We also have annual memberships, and we do have donations. Without all those, we have, I put together our list of everything, the least necessities of what we need to do to run our websites and our servers and our subscriptions to our software, etc., and this service like StreamYard, and that comes out to be about $2,300 a year. So we do need your support. Please think about becoming a member or make a donation. Your support is literally vital to this group. And I do want to thank Nick Percival, Dr. Cynthia Whitney, and Ramsey, and all our monthly members. And we do, again, need your vital support. So please think about that. Coming in this year, we have, of course, invited guests like we have today. Next week, we're going to have, oh, well, talk about that. Read the slides, Dave. Stick to the slides. The best of the CMPS conference talks. We're going to have people come on and talk about them, because there's some really great talks out there. It's been a while, and we have a lot of a new audience out there. So we're going to take a look at that. And we're going to also look at new dissident science, new takes on the world out there. We read a lot about science, and it's very interesting to get our takes from critical thinkers outside the mainstream when we read crazy things like multiverses and those kinds of things, and time travel, etc. And we also knew historical perspectives in science. In fact, next week you want to tune in, because we do have Eric Reeder, and he's going to be talking about the history of quantum mechanics. He's one of the experts in our group who knows and works with quantum mechanics quite a lot, and we're very happy to have him talk on history of quantum mechanics. The week after that, I'm going to talk about a little bit about the philosophy of why the majority is always wrong. It's going to be really great. One of the problems is, of course, people come in and they want to debunk people who are outside of mainstream and say, of course, the mainstream, and if it's not in the universities and the libraries, then it's crackpot, and actually that's not true at all. So I've got a really good talk lined up for that, why the majority is always wrong, which is quite good. And we have, of course, we're going to have debates on special relativity, general relativity, dark matter, and more coming up during the year, so you don't want to miss that. And the history of general relativity, light, magnetism, electricity from a distant point of view. And of course, we do have speakers that we line up all the time. So today we're going to be talking about the particle model and electronic circuits. We are giving a book away. We have people, if you want to send an email to us, you can send it to david@dhilster.com. You can find my email everywhere. Just Google David D. Hilster. You'll see a bunch of websites. It's got, you can find it very easy. Send us your one sentence definition of what the particle model you think it means. It doesn't mean you have to agree with it at all. You can think it's garbage, but we're wanting people to give us their ideas. So you can send us the contest in your own words. Describe the particle model. We'll be reading them, and you must not be an owner of the book because you won't get the book, but we will be sending it to you anywhere in the world. And yes, we have shipped our books to Africa, Europe. People have bought our books almost on every continent. So I know in Asia, Japan, I think we've sold some books. So thank you so much for your support. But if you want to win a book, an ebook, or a paperback, send us your description of the particle model in one sentence. Okay, just to give you a brief overview again, the particle model is really a movement classification, meaning the entire universe can be described in these four movements. You notice there's not any for ether. The gravitic one is not ether. It's actually just particles. It's the same as the graviton, which we know, of course. Magnetism is just orbiting particles. Electricity is particles going in the same direction. And light, luminic, are particles in waves that have a frequency traveling together at the same speed. It is a big picture model. I think people sometimes get all, bent up on the details, and what really, in my opinion, is about the model. It's really the first model to give physicality to everything, and I mean everything. One of the things that people were getting really mixed up on is they think that, for instance, maybe the particle model is only one particle. Actually, we have an infinite amount of particles. So I put together this chart. This is new. It's going to be in our new revision of the book. They got the standard modern ether, not old ether, but modern ether, and then the particle model. The electron, of course, is a particle with the magic charge of negative, which is magic because there's no physical explanation for it. Modern ether, they don't really talk about the electron. Closest I've seen come to that has been Glenn Borkert with his ether saying that, and Yonel Danu saying that it's just waves. It's just like light, but it's captured and stays in the wire. Of course, they can't explain how that keeps in the wire. In fact, Yonel Danu does say that, but it's he uses electrogen, makes up a new element in the periodic table that he says there. Then a particle model, of course, the electron is not one-to-one. The G1 particle, or what our particle at the one level, is not one-to-one. We're pretty certain that there's a lot more particles per what they call one electron, that it's not really one particle, it's a quanta of particles, and that's in our model. Photon, of course, is a particle which they don't have. Of course, it's a wave, it's a particle, so that's quite, how do you say, difficult to describe. Of course, a modern ether, and all of ether, is basically giving physicality to, number one, light. Gravity is a secondary thing, but number one is light. And then, of course, in our model, we have the same particle for all four of these. The graviton is postulated by the standard model, but it has not been found or verified. Modern ether, a lot of etherists, not all of them, will try to describe gravity using the ether particle. And, of course, we use the same particle for electron, photon, graviton, and for magnet. And the magneton, I made that up. That is Dave D. Hilster making them up. There is no such even concept in standard model. Modern ether, of course, you have Yonel Danu, who came up with the idea, which we actually use his idea, which is the flowing in loops of they say ether particles, and then of course ours is just orbiting particles. So we in the particle model we have all of these as one particle. If you look at the modern ether theories, with 90% of the people here are etherists, you're basically doing pretty much the same thing. So this is no big departure in any way. It's the difference is that we do things very differently. We don't have a medium. We have particles that are always moving in straight lines unless they're hit. The proton, neutron, of course, in standard model, you have the magical plus on this and a neutron, which is nothing there. Modern ether, they don't have it. I know Franklin Hugh puts the electron together with the proton, I think, and makes an ether particle. So yeah, there's different variations. And we do have a nucleon. That is, there is a nucleon, so that's two particles so far. The particle count in standard model is 17. Modern ether, a lot of people really don't have a count. Or you're like Borkert, which has an infinite amount because there's no elementary particles, and that's the same way with us. We have an infinite amount of particles. There are really four local particles that we really look at, G1 and the nucleon, which do pretty much almost everything we're seeing, almost. The G2 particle, which is really involved, is in the Coulomb force, which is just another gravitic force, and G3, which makes the G2 run. And of course, elementary particles means they're not divisible, which in many of our thoughts does not exist. But there are modern etherists who also have elementary non-divisible, and you have the no because of Borkert. And no, none of our particles anywhere are elementary and don't have a particle. We do have a numbering system. The gravity particles go from GC, GB, GA, G1. We live in the one level. So we live in this level. These are higher levels where things get bigger and glom together, and then we go further down to subparticles and subparticles. So G1, G2, all the way to GM. Average speed of the GN particle is, we call it C1. So C1 is what we would translate into C, but we also contend there's the speed of the other particles at the other levels, and they get much higher, and they go much lower in this direction. Nucleon particles, that is things that get orbited like a planet or a sun or whatever. The levels above us, again, N1 is our current level, at levels below us. Atoms, again, same numbering system. A1 is the atoms we know. The periodic table, and we're in P1. We all know our periodic table in P1, but there, who does this also a periodic table, subatomic, very, very nice model, Jeff Yees, and he is an ether model. Explanations, level B are galaxies. You have a periodic table of PB, of B level of periodic table of galaxies, Halt and Arp. level A is suns, planets, moons, comets. It's a periodic table of celestial bodies. I don't know, yeah, I'm making these up in the sense of that's the way our model works. I haven't really sat down and classified these things in any way. Of course, we have our regular periodic table, and a subatomic and Coulomb force is a G2 particle and N2 particles, and there's a P2 periodic table, and on and on and on and on. Okay, and the characteristics are G1s can go through and hit a GA. What's GA? Ourselves, goes through the, hits and goes through the Earth. An N1 as nucleus, it also hits those. Oh, it doesn't go through the N1. That's wrong. Oh boy. It doesn't go through the N1. It hits the N1. Oh yeah, okay, it goes through the G1. Okay. Sorry. I won't correct that, but yes, I will. Okay, so it goes through the GA, hits the N1. There we go. Goes through G1, goes through G2. Don't you love live stuff like this? You can just do that, save it from the current slide. Voila. Oh, now it's right. Okay, and we put these together last night and this morning. So, and here you can see what can happen. You can have something pass through a particle. It can hit a particle and go into orbit, or it can just simply curve around it, all because of gravitic fields. And we're going to talk today about electronic components. So I wanted to go through really quick with electronic components. People probably want to know at the GA and G1 levels. So at the GA level, you can think of comets as being electricity at the A level. And sun. So you can imagine the way you can picture and hack the universe with the particle models. You can put in, this is what I do. I look at the suns. Okay, if I put all the suns in these formations, then I could guide comets very easily. I could make it so that when I threw a comet down, it would just stay in its path because of the G1 gravitic field, what we call gravity, our G1 gravity. Then you can go down a level, shrink yourself down to smaller than the size of the atom, and now what you're seeing are nucleons, and these nucleons are just like the suns, and the G1 particles just like a comet, and the only difference is you got a G2 gravity, which goes even faster and is smaller than the G1. It's a different particle, and that keeps things going, and that's how in our model, electricity works. In fact, the magnetic field around the wire basically happens because of what we say is the nucleon positions in copper cause a spiraling of the G1 particles. Yes, they go through metals. Metals that are good conductors are set up in a way so that the G2 gravitic field keeps them all in line, and that, that's the property of them. But some of them start to spiral around, just like if you were to have these, and these are all suns and these were comets, you could easily see that some of these could get outside and spiral. So yeah, you have magnetic flow. Basically, it would be like trying to find, you'd have electrons outside the wire as well, but we call magnetic fields. They're not electrons, they're G1 particles. They're probably way smaller than an electron. So that gives you an idea of electricity going through a wire in a magnetic field. Finally, before we get to my dad, I was going to talk about experiments with this. I thought this is in our book, gives you an example of how all 4 particle movement classifications. You got orbiting G1 particles around nucleons in the battery, which get funneled through the copper wire, just like suns are, and they go flying through here. They're just basically electricity. There's no modulation or there. You talk into a mic. This is a circuit for an FM transmitter. Talking the mic, basically a mic is like pushes these things literally out of the wire, and you're left with a luminic or a waves of particles that have information about the sound coming in and knocked out. There is actually an inductor in this. This is just for demonstration purposes. It's not important that you know how it works, but there is magnetic fields inside of FM circuits. So again, we have orbiting, magnetic, electric, and luminic all in one. Gravitic field is G2 field causing the G1s to orbit here and stay in the wire. So G2's gravitic is all over the place. And those signals you can see here modulated go out. And instead of an electron going up in an atom and coming back down and then emitting a photon, and no one knows what the heck that is at all, in our model it's easy because electron, photon, graviton, magneton is all the same. So it's basically, yeah, It comes in and it goes out. Yep, that's how it works. So, anyways, that gives you an idea. Let's talk about my dad. This is his lab again and his room. He was born in 37. He's age 84 from Wyandotte, Michigan, retired electrical engineer with a degree in engineering physics from the University of Michigan. After graduating in 1960, he worked on the UNIVAC Zero computer at Remington Rand. He spent the majority of his professional career developing digital switching systems for telecommunications. In 2006, Robert helped conduct an experiment as described by physicist Dr. Ricardo Carrizzani designed to detect existence of gravitons. He was the main character in the documentary film Einstein Wrong, the Miracle Year. During the filming, Robert developed equation for gravity. 2015, he came up with a solution to the wave-particle duality and wrote a book with his son David. That's me. Today, he is working on a second book entitled, the Physicality of Electronic Circuits, where he has shown experimental support for two predictions by the particle model. So I believe that's my last. Yep, that's my last slide. So I will bring that down and I'll bring my dad up. Hello?
Hey, can you hear me?
Hey, I can.
Anybody else hear me?
No. So, you want to tell them what, I guess in your slideshow, you're going to be telling us what's going on, except I don't see your slides.
Well, I have to bring them up almost yet. I don't
Oh,
know.
okay. All
You got
righty.
you got them now?
I do have them now.
Does
So,
everybody else have them?
yes, they do. So I'm going to let you go and take it away.
Okay. Welcome to my talk on TPM experiments. I am going to go through an introduction to start with, and then I'm going to talk about experiment 1 and experiment 2. And I apologize for any redundancy, but in terms of the introduction, I am going to talk again about what the universe is made of, but kind of focusing on how it is used in electronics. And then I'm going to talk about charge. And then, Bob Gray, I just left you a message. After charge, you and I are going to discuss your drawings. So we move on. What is the universe made of? Particles, particles, particles. There are two particles at each level of the universe. It starts simple, but then the model suggests there must be an infinite number of levels, which Dave just talked about. For the purposes of this presentation, only two levels are used, level 1, level 2. Now, level 1 has the G1 and N1 particles. Those are the two in that level. G1 is like the electron, but with no charge. The N1 is like the proton, also with no charge. Hydrogen has one G1, but maybe more than one G1. When it gets down to getting details about the atom, we're not sure, but there are experiments that would indicate that maybe there's more than one. But that G1 or however many, they orbit the N1, and that's what you see down here as a level 1 atom, N1 nucleon, G1 orbital, we call it a G1 orbital, orbiting around, and it makes the level 1 atom. The speed of the G1 orbital is, we call it C1, Dave said that, and it's very much like the speed of light, but maybe more, maybe less. This concept is extended to all atoms in the level 1 periodic table. Yes, that's the table we know about. All these atoms are made up of N1 and G1s in some combination, like the Bohr model atom, but not exactly. We think there's more variations than what the Bohr model would indicate. Level 2 is a level down. Level 2 also has two particles, the G2 and the N2 particle. The G2 orbits the N2 and is one of many possible atoms of level 2. Don't know anything about the atoms of level 2, but there must be one for there to be a G2 orbital that's moving faster than light. The speed of the G2 is C2, and we're saying it's faster than light because this is so much smaller than the level 1 atom. The particle model strongly suggests that there is a subatomic atom that is smaller than any of our atoms in the periodic table. There is no physics theory that has a subatomic atom. Modern science comes up with more elemental particles, not atoms. But as you will see later, the bending of light and the control of the G1 particle flow by a particle in our model requires that this particle be faster than light. And that particle must come from a subatomic atom. Otherwise, this doesn't exist. And yes, our particle model wouldn't work without it. Okay, so there are more gravity levels. It turns out that the G1 particle field around the Earth is the field that causes the apple to fall to the Earth and the moon to orbit the Earth. This is similar to Newtonian gravity. It is the G2 particle field surrounding level 1 atoms that keeps the G1 in orbit around the N1. So level 2 gravity is required to support level 1 atoms that are in our periodic table. Gravity 2 plays a primary role in electronics. I almost never mention gravity 1 in electronics. And so there must be a level 3 that has a G3.
Dad, I'm going to interrupt there too. We can also say that G2 particle fields like coulombs, right?
Yeah, exactly. I didn't make that correlation, but that's right. So there must be a level 3 that has a G3 that keeps the G2 in orbit around the N2, a subatomic atom. Continuing this logic will lead to the conclusion that there are an infinite number of levels, both up and down, as David said. There is indirect evidence of level 1 and 2. I'm claiming we have indirect evidence of level 1 and 2, but not for level 3. Fortunately, level 3 is not used to explain the physics when using the TPM model. It's a requirement of the model, but there's no evidence, direct or indirect. Okay, charge. We claim that G1 does not have a negative charge. A negative charge is rejected because science has never described a physical property that makes a particle negative. And it's the same for the positive charge. But further, this is something I actually just recently came upon, and I have a video out called Charge, a Contradiction. And it basically talks about this situation here. Further, there is a conflict between the concept of EMF, electromotive force, versus the concept of attraction repulsion. Also, there is no physical explanation of what EMF is, nor what causes attraction and repulsion. So there's no physical description, and they just say it happens. Modern science tells us what it does, never tells us what it is. So let's go through the contradiction. So we start with the battery here. The vertical arrows pointing down is the EMF, the electrical field, which pushes the electron out to the negative port. Now, current's shown this way, but the electron goes the other way. So the EMF here works quite well. It pushes the electron towards the negative end of the battery and out. So let's look at EMF on the cathode ray tube. Now, you won't find EMF shown here. I had to add these two arrows and this E to show that there's an electric force from the positive to the negative plate. So there is an EMF force here. So if the electron is pushed out the negative towards the negative in the battery, shouldn't the electron be pushed towards the negative in the cathode tube? It's not. The EMF force, it goes the other way. Here it goes towards the negative. Here it goes towards the positive. That's a contradiction. Now, if you come over to this one and you use attraction and repulsion, yeah, the negative electron is attracted to the positive plate. That works as long as you accept the idea of that concept. But you come over here and you look at the electron. If you use attraction and repulsion to explain this, it ought to go up, not down. That's a contradiction. So what modern science does is they'll use EMF here to explain it and ignore attraction and repulsion. And you come over here, you don't use EMF because it doesn't work, and you use attraction and repulsion. Totally inconsistent. Which says charge is not real. I saw a comment by one of our visitors. I think his name was Toby, and he says, this model, these experiments are going to prove that physics is wrong. When you accept the idea, or whether you accept it or not, TPM says charge is wrong. That really knocks the underpinnings of modern science. It really is devastating, because you get rid of charge, you don't have a standard model. Okay, I'm going to go ahead with comments or questions if anybody wants to make a comment. Levels 1, 2, and 3, particles, 2 particles per level. We're saying there's a subatomic atom. We're saying charge is wrong.
Okay, there's a question here, Dad. It says, I was wondering if your particles have different sizes. The big question is, what are your particles made of? I think we've already talked. You talked about that already.
Well, I'm going to go into it exactly here, because Bob Gray, I promised Bob Gray that I would address his. If you could pull Bob Gray up and have him comment on his email that he sent me. This is the figures in the email. Bob, are you there?
Hi. Can you hear me?
Yeah, I can hear you.
Good. So my question was about the reality, the physicality of your electric field and magnetic field in your model, and how is it explained in the G1 model?
Yeah.
In particular, I noticed between parallel plates, if you take a very small region, they say the electric fields, if you drew the field lines, would be straight parallel to each other. You put a charged body in there, and that will move the charged body. On the magnetic side, which I have on the right, that figure, if it's a long, tightly wound solenoid with a DC current through the wires, the magnetic field in a very small region in the center of that solenoid, those field lines would also be straight and parallel. But you put a charged particle there, or a charged body there, and that charged body won't move. And so now it seems to have a contradiction. In one case, you have G1 particles moving, interacting with a charge and moving that charge.
Exactly, you're right.
In the magnetic case, you have G1 particles moving again, but it's not moving the charge. So
I don't get it. Well, I don't get you. I'm going to ask you a question back.
Certainly.
What's holding this in place?
What's holding which part?
The particle in place. What's holding that?
It could be a charged pith ball, which is a physically something you can handle.
No, that's what it is. I want to know, there must be a force keeping it there.
No. Why should there be a force there? I can place in a vacuum where there's no gravity, I can put a charge someplace and the charge will sit there.
Exactly, but this isn't a vacuum. This is a magnetic field.
Right, and that's my question. Why doesn't that charged body move?
And the TPM model would say it does. It does move, because you're right. There's G1 particles flowing here. If there's a G1 here, then you're going to have collision, and it's going to move it out this way.
Right.
But further, there is a gravity 2 force all the way around this, and a very strong force in this direction, very strong force in that direction. In fact, in all directions, such that the G2 gravity would try to hold this in its place, except G1 is coming along, hitting it, knocking it out. There may be a point out here where there's a balance between the G2 gravity this way and the G1 collisions that way, but generally it's going to be
Right.
gone. It's going to move.
Right. The standard physics would say it would not move.
Yeah, but in
Right.
our case,
And that's a distinction. I'm wondering if there's any experimental evidence one way, or could that be used as an experimental?
I really would be. I'd like to see someone take a charged particle, put it in that spot, and hold it there, let it go, and see that it doesn't move. That's really kind of hard to do.
Yeah.
I think the other part too, Bob, which is very confusing, is when one of the biggest things that I see with charge, moving charged particles, fields, electric field, magnetic field, is because because we have zero physicality for any of that. We talk about it as an abstract thing. We talk about, I mean, a lot of these fields, like an electric field, is talked about because we in our heads are talking in some symbolic form. We're not giving it any physicality. So when we hear that, in the particle model, it's like, no, you have to, in the particle model, tell me what particles are moving what and what is there. You can't just say the word electric field. Right, that's the problem. Electric field, magnetic field, a charged particle. Does a charged particle moving cause an electric field? All those kinds of things. The thing that I've seen for 30 years when I hear people, I mean, there's been, even in this group, we've had, Saturday session after Saturday session after Saturday session, talking about charge, moving charged particles, electric fields, magnetic fields, with never talking about what those things are physically, ever. And so what we're doing is we're talking about arbitrary attributes on arbitrary things without any physicality behind it. So when somebody with a system like that then comes to the particle model and says electric field, what does that mean? I mean, what does that even mean, right?
I don't know that I'd go that far because of, for example, you showed the cathode ray tube. So you know that there are such things as charged bodies. You know that they're discrete. You know they're moving, et cetera, et cetera. Now, what?
No, wait. No, wait.
Okay.
I know what you're saying. Charged bodies. No, in our model we don't have charged bodies. So you say
you do.
We know.
You have a plasma. No. You have a plasma of G1 particles.
But it's not charged. There's no charge.
That's right. Charge. It's G1 particles.
Right.
And that's fine.
Okay.
Okay.
Could I move things along because I think?
Okay, I'm sorry. Bob and I are having a wonderful time. Dad, hey, Bob Gray. We should probably let Dad go.
Yes.
No, but please, it's been an interesting. Sorry. Okay, I'll bring you both down and let him go. Okay, thanks. Very interesting questions, discussions.
All right, I'm gonna go. We talked about the magnetic part. This is the capacitor kind of a part here. This is the TPM explanation. We got G1 current coming from the battery flowing, and most of them pass right on through. Some of them get trapped as orbitals on the first plate, which we normally call a negative plate. Fewer of the G1s pass through here, so there are fewer G1s trapped in this positive plate, creating an imbalance here. So so in the particle model, it isn't that this is plus and literally plus and minus. This has a different number of G1 particles trapped in this one, and this is like a small mass, a G2 mass, and this is like a large one. It ends up being a net G2 gravity force, just like the electric force going from the positive plate to the negative place. So we have a force going this way, and that force can move particles. But we also have G1 flow going through here. The red arrows are just G1s that are flowing through and charging the capacitor, and many of them passing through, going around the circuit. So there are two forces in this capacitor. There's a G2 gravitational force this way, and there is a wind of G1 particles moving this way. So now what I can do is I'm not going to place them, try to hold them steady, place it right here in the middle. I'm going to do it like they normally do, where in a gun, where they shoot a G1 particle through here. Now we know the G1 particle, this fast G1 that's moving at speed c in this very short distance, we know that it moves towards the right. The only force I have, literally, this is what I had to say to myself. The only force I have is the force of the G1 collisions moving this way, countering the G2 gravity force going the other way. Those forces are acting. Both of them are acting. What's the net result? Well, the G2, this speed, this particle is going so fast, and this is such a short distance. My opinion, the F2 force is going to move it to the right, but very little. Where the G1 wind, if you will, that's pushing, wind like pushes a baseball. As the baseball goes by, you can actually cause the baseball to move. These G1 collisions are what causes it to move to the right. And your answer is, does the particle move? The answer is yes. In this case, the smaller, faster particle moves towards the plus plate. On the other hand, the N1 is a nucleon, is a very large particle. It moves slower, and because it's heavier, the collision force caused by the G1s have a harder time pushing it, but it does some. It'll push it some to the right. But the F2 gravity, since it's moving slow, will eventually override and cause it to go to the negative side. So you see, even with the TPM model, I have to get into a lot more detail to try to explain what's really happening when you shoot an electron through here or a proton through here, and why does it go the way it goes. Interesting final point. In almost all cases in the particle model, there are two opposing forces, and it's the one that's strongest for the various condition you're using that determines which way it goes. It's an interesting point. Even gravity, me sitting here, there's gravity particles pushing me up and there's gravity particles pushing me down. And they're still there. It's just that the net difference ends up being pushing me down. Bob, thank you for your question. I don't know if that, hopefully that gives the TPM explanation. You may not agree, but this is generally, by the way, this F2 force is the force that discharges the capacitor. Once the G1 flow stops, the F2 force starts pushing the G1s out the other way. That's the back EMF is sometimes called. Okay, on to the experiment.
Yeah, Dad, just to repeat to people, when you talk about the G2 field, you can substitute, if you want to look at the model, the mainstream model, it's a Coulomb force, okay? If you want to say something like that, right?
It's a Coulomb force without charge.
Right, I know, but I'm saying if you want to, in your head, kind of get what it is. I think problem with people is a lot of times they don't understand that what we're substituting for Coulomb force, which is just a, how do you say, concept with zero physicality. We're making that into a gravitic force with G2. So, okay, go ahead.
Okay, so I'm leading into the experiment number one, but I got to give you some background. Based on Lesage gravity, and this is a diagram of Lesage's type, my diagram, the gravity particle from Lesage comes at the object from all directions, not just from the left and right, but all the way around. Most of them pass through. That was his thought. A few of them will hit somewhere along in the path and scatter and be lost, leaving fewer here. So if you're standing here, this I just mentioned, you got some pushing you up, some pushing you down, but there's more pushing you down than up, so you end up with a net force of gravity. My point here is, as the G1 particle goes through the Earth and it happens to hit, you lose them. They disappear. They go off into the G1 particle field. Here's a resistor. G1, this is G1 current. This is a steady flow of G1 particles coming through. Some of them will hit and be lost. Most of them go through. Here is the thing that struck me immediately when I did this. When I looked at this very thing, the loss of G1s, I immediately corresponded to the loss of voltage. I'm applying Lesage's these principles. These are the same principles that we use for gravity. I use it for electronics. I use it for light through prisms. I use it for magnetics. It's the same theory applied across the board. Loss of G1s implies a direct loss of voltage. Amazing. So what do? You're going to get me for this one. Assign a voltage rating to the G1. If there were 100 G1s lost going through this resistor in that 10 ohm resistor, then the G1 can be assigned a value of 0.1 volts. If there were 100 lost in a 10 ohm resistor, I could assign the value of the G1 as having 0.1 volts per G1. The G1 does not have a physical property that gives it a voltage value. It's only the correlation that I just showed you in the previous slide. The electron does not have a physical property that gives it a negative charge. These are assigned values. I'm assigning it so I can relate the physical property of G1s going through the resistor, losing some, and be able to correlate that to the voltage drop. That's all I'm doing. So I make this assignment, and I stuck with this pretty faithfully throughout. Okay, TPM analysis. If the R1 loses 100, the battery must add 100 to match Kirchhoff's voltage law. If the resistor loses G1s, then the battery must add. That is, if I start with 0, I add 100, I lose 100, I'm back to 0. That's a stable circuit. The gain and loss of the G1, I should not use electron because I'm talking G1s. Gain and loss of the G1, this whole thing is a whole new concept that I never was taught. I didn't know until I put the G1 through the resistor, treated it just like the G1 through the earth, and I come up with this comparison, and it's amazing. It works. It's just amazing how well this works. Well, this is my experiment, my first one, and I'm going to compare voltage losses in this circuit. And I literally used a 9-volt battery, a 4K resistor, at least in my initial analysis, a 3K resistor, a 2K resistor. And if you assign this number, this is a man-made assignment, a Bob D. Hilster assignment, that each G1 has a 10-volt rating, a tenth of a volt rating, then a 9-volt battery must be adding 90, losing 40, losing 30, losing 20, and you're right back to where you started. That's a stable circuit when the sum of these losses match the sum of this added gain. Well, like I say, we've never taught that a battery adds G1s or electrons to a circuit, but that's what TPM teaches. Okay, so then I have to do the experiment and make predictions. I got to do calculations, and so now I start with how do I write the equations for this? It's not like, yeah, I can, in one sense I do use Ohm's law, but I got to account for the gain and loss of the G1s. So what's the value of B? B is equal to A plus whatever is added. And that whatever the battery voltage is divided by VG1 is the number it adds. 9 divided by 0.1 is 90. C is equal to B minus the number lost through resistor 1. D is equal to C minus the number lost through resistor 2, and so on. Those are the equations, and I finally end up with E, which should be A, but A starts the next cycle. So I do these by cycle, as if there was a small interval of time over which, okay, I release 90, I come around, maybe that's 1 nanosecond, and then another nanosecond. So this is 1 nanosecond, the next cycle is another nanosecond. That's an arbitrary number. Okay, so to finish this equation, I got to have an equation for the number lost in resistor 1, 2, and 3. The number lost in resistor 1, I'm claiming, is proportional to the number entering, the number of G1s entering times the value of the resistor. Lost proportional to B. B is entering to R1, and R1 is the value. It's a proportionality, it's not an equation. So I introduce a new factor here. The interaction factor is a constant of proportionality that helps determine the number lost. IF. So now I know the number lost is B for R1 is B times IF times R1. And I insert that. I change the number lost term to B times IF R1. This is C times IF times R2 and D. So I now have a set of equations. But what about this value? Well, I played around with this a long time as to find out what kind of a value would be. I picked this number. I picked this number because of the thing I worked with. You just have to trust me. You can pick your own. I'll tell you, you can pick your own numbers for VG1 and IF, and it'll still work. You pick your own numbers. So I picked 5 times 10 to the minus ninth, and it has the units of 1 over ohm because B is the number of G1s. This is in ohms, so this has to be 1 over ohms to make the units work. So you go through the one cycle, you find E, and then the next cycle you do that, and here's the spreadsheet calculation. I started with A equal 50, arbitrary number, VG1, voltage is 10, it adds 100, B then is 50 plus, that's 150, because I hope you don't have trouble with reading exponential, but that's really 150. This is the interaction factor I just picked. That's the resistance value. This is the number lost in resistor 1. C is equal to B minus the number lost. And I got C. Normally what you would do is you would take C and put it over here in this slot. But I didn't do that because it would take too many cycles. I couldn't get, there'd be, to be honest with you, there'd be 13 million rows I'd have to print out. So I pre-calculate a K value, which is the value of 100 divided by NRL, and that gives me, that's 13 million. I multiply K times 50 and I get a new number, run the cycle, do the same thing. This time I'm off by only 3. I multiply this number by 3, I get this. And now my factor is 1, and I'm stable already here. After 13 million cycles, I'm stable. And what it says is, based on these numbers, VG1 and IFR, that there are 2 billion G1s going around that circuit constantly.
Dad, maybe you can explain a little bit what the cycle means. To make sure I understand it too, obviously, is that you, for this model to work, you can't just, it just doesn't turn on and it's instantly to its final state, right?
No. What I'm saying is I have to do this. I can't do it instantaneously. Maybe I could use calculus or differential equations to do it kind of in where I could take time and reduce time down to almost 0 and then sum it up that way. You get the same answer. I'm using this as a discrete analysis, saying I can break this into a small interval of time, 1 nanosecond around, and calculate what would happen in that nanosecond. And then it adds again another nanosecond. That's a discrete quantized calculation to make it a lot easier than having to try to figure out a new math or use calculus to do it. So I'm taking it in very small intervals of time, basically one loop. This is 1. If it took 1 nano, if this is moving at speed c, it might. I made an estimate on my circuit how big it's a 4 by 4 square inch circuit, and if it's moving at speed c, I got close to 1 nanosecond for 1 particle to go around 1 time.
So how many times? Okay, so how many circuits around I mean, how many times around the circuit to get this stable? You said 13 million.
13 million
Okay.
and three. 13 million and three. Yeah, and so what? How much time is that? You know, I don't want to get into some parasitic capacitors, but there's another thought I had there. So this is the type of spreadsheet calculation I'm doing. Now I'm going to do it. Oh, by the way, this time I didn't use 50. I used 500 billion to start with, a very large number. I said, let's assume A is very large. And I go through and do the calculation. Well, when you divide 100 by the number lost, the loss is huge. You get a very small factor. You multiply the factor times this 500 billion, and you get this number. And in a very short time, you're stabilized. So no matter whether you start high or low, and I've done this with the spreadsheet. I've done it without the K factor, and I set this number just above the 2 billion. Okay, set it just above, and then I make C go to A for each, and you can watch this thing go up and down trying to find the answer, but hovering, if you will, right around the stable point, which means that the circuit it's stable, but it's a dynamic stability when you actually when you don't use an accelerated calculation.
Okay, there is a question I just wanted to sort of put up there. It says, does the battery store G1 particles, or is it pushing it around the circuit?
There is a just like the capacitor has a G2 force, because the battery has a smaller number of G1s here and a large number of G1s here. Zinc is much more active than copper, so you got more G1s here and fewer. It creates a F2 force here, which pushes them out. As the battery releases it pushes it out, and whatever comes in, most of them pass through. Some of them don't pass through, by the way, and that's where you get the resistance of the battery into play. When the ones coming in actually hit and lose, that's the battery impedance. I don't know if I got the. Maybe I'm rambling here,
No,
but
that's right.
the battery does set up a G2 gravitational force, just like the capacitor, and it pushes them. That's why the G1 goes out the tail end, because this has very few G1 particles. This has a lot. There's an internal force, just like the EMF pushes them out, come around. And this one adds 100, this one loses 100. And that's what you end up down here. This one adds 100, this is losing 100, and it's balanced.
I think
But
the other thing about circuits in general is that it's very common in our model to have G1s literally thrown out of the circuit. They're gone. They're out in space.
They're out in space, exactly. Okay, now the experiment. I'm doing a voltage experiment. I'm going to tell you what the experiment is. Just trying to get the equations, the spreadsheet. The spreadsheet I use for this calculation is much more complicated. I can't fit it on the slide. The 4K resistor here in the first location, R1. I'm saying this is a prediction. R1 will have a larger voltage here than when I put the 4K up here. Why? Because I'm losing G1s as I go around. I have B is a larger number than D. So there's a bigger voltage drop here. When I put the 4K up here, is a smaller voltage drop. Same thing with the 2K resistor in this last location. Will have a smaller voltage drop than when I put it down here. So that's exactly what I did in the experiment. I started with a large, medium, small resistor, put them in this location, did all my measurements. Then I switched the two and I did the measurements again. Okay, and I'm expecting that in this position, they will be less voltage drop here than there is down here. So what I did was pick 15 sets of resistors. I selected 15 sets with different values and ratios, not just 4K, 3K, 2K. Measured the voltage loss of each resistor in the first position and then when it was in the last position. Then I calculated, went to this spreadsheet. I entered the measured value of the battery voltage and resistors into the spreadsheet so I could make my prediction realistic about concerning the particular set I was at. From the spreadsheet, I can calculate the voltage across by multiplying the number lost on resistor 1 by VG1, I get the voltage drop. The same for VR3. For the voltage, when I put the 4K in the third position, I multiply the number lost from my spreadsheet times VG1 and I get the voltage drop. So I have a measured value of voltage, I have a calculated value of voltage, and I compare them. This is the result. Here's the measured value, the first three columns. This is the 15 circuits, all different values, different ratios. When the large resistor, this is all about the large resistor, when it was in position 1, it had this voltage drop. That's what I measured. When I put it in the third position, I measured this. All I did was subtract it. I'm expecting a positive answer. Whoops, right away I get a negative. But I'm doing it for all of these. So when you just look at this, I've got 1, 2, 3, 4 that are negative and the rest are positive, just like I predicted. Not 100% here, but that's what the measured values. But then I said I took the measured values of the and put it into the my spreadsheet, and I got these numbers. Well, look at here. This says it ought to be positive. Well, clearly this is wrong. No matter what I say about circuit 1 didn't give me the right answer. So of all of these, this is wrong. But look what happened here in circuit 7. I measured a difference of a negative, but when I put that into I calculated my my TPM actually predicted it should be negative, even though I thought it should be positive. The circuit after it stabilized and did its thing, it said, no, this one, because of the values you picked, this one's negative, this one's negative, and this is, even though these are red, these are matched. There's only one wrong here. There's only one wrong, and that's circuit 1. That's a 93.3 comparison, showing that the voltage across the when it's in the R1 position is larger than, if in most cases, is larger than the when it's in the R3 position. But even the prediction will predicted the negative measured result.
There's a question here. Was a nanometer use 6.5 digits?
Yes.
Was it 6.5 or 7.5?
No, I rented the Keithley 6.5 for the first experiment. I bought a Keysight 7.5 for the second experiment.
And one of the I think part of this is, and these are things that are just would be general questions too, is that why would this not be seen, these changes in current, right? And and then one of the other questions is, well, why would somebody even have a voltmeter to such a ridiculous length? I think those would be two normal questions. Maybe you could answer.
Okay, the company Keithley and Keysight make instruments for other companies who make meters. If you want to buy a 3-digit meter to use at your home, the company that makes that will use a 6.5 or 7.5 digit meter to make sure their meter that they're selling you is accurate to 3 digits. So it's used in what's called metrology, meter testing and design. Okay, what was the first part of the question? It's about why wouldn't you measure this? I do come to that. I'm going to answer that question, but at a later slide, if you'll allow me, because I want to move things along.
I do, but there's another question real quick. Very simple. Was the circuit held at a constant temperature?
Room temperature, yeah. It wasn't. I did make sure that the wattage ratings were not exceeded. The rule of thumb in electrical design is that if you need a 1 watt resistor, you put a 2 watt resistor in its place so you don't have temperature problems. But otherwise, it was room temperature. And in this room, it was air conditioned pretty well during that whole time. So, and it was on and off, so there was temperature up and down. Yes, to some degree. Okay, how about the small resistor? Did the same thing. Small resistor. When it was in the first position, I measured in the last position, and I'm expecting positive. I get a negative here, and I said, "Oh, that's wrong." Oh, then I should have started putting red on all of this. Look at, I was expecting it to have a larger voltage drop in the first position and a smaller one in the third position, and they all came out negative. The only ones, this one was wrong here anyway, but this is the only one that came out positive like I expected it to. Something's wrong, but I did the same thing. I used my equations, and when I plugged in the values needed to run that sheet, the prediction is negative all the way up and down. There's two that are wrong. C1 is wrong because this said the prediction is positive, it came out negative. This says it's negative and it came out positive. So there's two wrong in this one. And I was shocked that this came out predicted negative and measured negative. And I think my next slide talks to that point. The reason I got the wrong answer is when I'm using this was circuit 1, was a 10K, 5K, 1K sequence, and then I switched the 10K and the 1K, and at 1K, and I copied down for you the value of the number of G1s flowing in that circuit by that calculation. And what I didn't anticipate was that the value of the number of G1s flowing around the circuit would change. Intrinsically, I'm assuming it without even thinking about it, that the number of going around that circuit would be the same, whether I had 10K here or 10K there. I thought it would be the same as not. Well, you could say, well, it's not a lot different, but it is different, and apparently enough to make my prediction incorrect. But that's even more amazing to me, that I predicted one thing and the equations predicted the opposite, but the measurements agreed with the prediction of the equations. Absolutely amazing. Okay. Cover G1s lost through a resistor are equivalent to a voltage drop. G1s added by a battery are equivalent to a voltage gain. And I just gave you the results, which were anywhere between 86 and 96% effective, showing in my mind, current is not the same going around. And because the current's not the same, the voltages are different. 4K voltage, the voltage across the 4K is different. Standard technology says otherwise. The standard answer is the current is the same, and the voltage drop of 4K, no matter where you put it, should be the same. And it's not.
Okay, there is a question. It's a little off, but I mean, I told them that you had this answered in some of your own videos. Again, if you want to, you can see Bob D. Hilster's videos. You can go to youtube.particle.guru and go to his YouTube channel. But the question again was, in DC case, electrons move at micrometers per second, and AC electrons don't go anywhere. I mean, that's a common thing. I mean, being an electrical engineer, I mean, what would you say with those kinds of?
Okay, the standard answer for a electron flow is that it's the valence electron that moves, and it moves very slowly from one atom to the other as it literally, if you will, hops from one valence band of one atom to the valence band of the other. Particle model totally is rejecting that. The battery is emitting G1 particles. They're spinning at very high speed when they're in the battery, almost the speed of light. And as soon as
They're orbiting. Wait, be careful, because people take spin as the particle spinning.
yeah, okay. They're orbiting at a very high speed, and as soon as they're released, they're going to move at high speed. And if there's open space, they're going to move through the open space. So it's a totally different concept. The electron in the particle, the G1 in the particle model isn't the motion of a G1 orbital from one atom to another G1 orbital. It's moving through open space at speed c.
Okay, the other question was about AC. Electrons don't go anywhere. What happens in this model? Just a quick answer. I know this is a little off, but
well, it's the same as DC. The only thing difference with AC is you got a half cycle going one direction, and the other half cycle going the other direction. Otherwise, it's the same motion. They say the electron doesn't go anywhere because somehow if you can keep track of one electron in a valence band, it moves this way a little bit, and the next half cycle it moves back. I mean, when you think of that current is the motion of the valence electron, that's what you get. That's what you're taught. TPM isn't teaching that. TPM says you have a high-speed orbital in the source or battery, and it comes out at high speed, and it moves through open space. Two different concepts.
okay, another question. What was the battery type and voltage that you had?
Oh, it was a night. I don't know.
No. Well, in your experiment, Dad, don't you have a power generator?
I have a power supply, but no, with that first experiment, I literally used a 9-volt battery.
Okay. Oh, and then high speed, you've already answered that. That's basically close to the speed of light. Well, actually, the G1 particle actually travels at the speed of light or slower or well, maybe even a little faster, but it is variable.
It's variable because the G2 gravity that pushes that out of the batteries is accelerating it. Come on.
Right.
It was orbiting at one speed. It's accelerating as it leaves. Yeah. It slows down as it, well, there are other criteria. That's later.
Okay.
Experiment number 2. Well, so number 1 had to do with voltage. This has to do with current. Now I'm going to emphasize the current. And I had a separate motive for this particular experiment because I was really trying to find a true value of VG1 and IF. And I hate to say it, my last video I reported the value of VG1, I failed. I didn't get it. But this is the circuit I was using to do that. And the way I was doing it is I put a shunt resistor here, a 1 ohm shunt, a nominal value of 3K of 3.9, 2.2, and 1K here, and another 1 ohm shunt there. Now, what I wanted was I want to know the current going in, the current going through, and the current leaving. And I was going to use that data to find these values. So here's what I did. I measured the current before in the S1, during with the R1, and after with the S2. The S1 and S2 were 1 ohm, 4 ohm watt shunt resistors. They were 4 watt resistors. I want to make sure they wouldn't get too hot. And then I selected 3 different resistor values, 3.9K, 2.2. I wanted 4, 2, and 1, but that's what I got. And this time I do have a power supply here. And my power supply, I'm able to set it up anywhere from 1 volt to 30. I use 5, 10, 15, 20, 25, and 30 volts. Now keep in mind that the current reduces, the number of G1s reduced. You lose some here, you lose some here, you lose. So this is what I'm expecting to see by measuring is a reduction from here to here to there. Now I'm actually going to give you the answer before I go through the details. So there's three sets of equations. And the current in the standard equation says if I take the battery voltage and divide it by the sum of the resistance, I get the current, and that current is here, 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 and they're all equal. So if I were to plot the current through the S1, R1, S2, they're all equal. In this case, it happened to be 1.5 milliamps. Okay, I'm just saying there's the standard equations. That's what they would tell you. Question would be, what do the measurements tell me? TPM equations. This is the ones I just talked about. And in this case, they should be going they should be going down constantly. From here, the current here should be higher, this should be lower, this should be lower. That's what I'm expecting. Okay. Now this one I have introduced, I'm going to talk about the speed factor, but I had to modify the equation to accommodate a speed factor. And now something strange happens, and I'm not going to go into the detail, but this is the summary result. This is the result of what I got from this test. If you use a standard 3-digit voltmeter, you're only going to see the three most significant digits of the current, and you're going to measure this. You're going to go in the lab, you're going to take your meter, you're going to read it. Okay, yeah, it varies a little, but basically it's generally constant. The equations say it's absolutely constant. Whatever the voltage is, you divide by the total resistance. That's the current to each one. But I used a 7.5-digit voltmeter when I had no speed factor, and this is what is predicted. It's high here. Frankly, it's a little lower here. You can't see it, and then it's lower again because S1's a small resistor, R1's a large resistor, and this is small again, and so you get this curve. I measured using this. I measured. This is the calculated, predicted. This is what I measured. Totally wrong. This prediction is wrong. This prediction is right as long as you use 3 digits, but this is wrong. This, by the way, but I'm not measuring 1.5 milliamps. I'm measuring 3.8 milliamps, and the difference is out here, 84, 82, and 80. This difference is in microamps, and that's why I need the 7.5-digit voltmeter. But the measurement says this. It's wrong. I knew there was something wrong. I had to find another answer. So I added the speed factor. I showed you the equation briefly. Did the prediction. The measured value is in blue. This is for circuit 1, 15 volt, where I combined the measured and the prediction, and they're practically on top of each other. I'm doing this because it helps explain why 3-digit meters read what they read and why I'm with a 7.5-digit multimeter are getting something different. This is at the milliamp level. This is at the microamp level.
Now, Dad, you being an electrical engineer and that very first one with the 3-digit voltmeter, right?
Yeah.
Pretty much, obviously, you spent 40 years of your life in electrical engineering. Very successful. With the 3, right? But you were very successful, and you used equations. So yeah, I mean, the equations in this case were empirical, really, right? They're not. They were. So the equation that says it matches the 3-digit voltmeter is not because if they would have a 7.5-digit voltmeter and measured what you measured, then they'd have a conundrum, right? Then they'd have a problem.
Yes.
So really, the history of electronics is that, well, we don't have any physicality for anything anyways. We have this old problem of the valence, the electron going in one direction slow, but the current in the other, et cetera, and we know it's going way faster than the electrons. It's got all that problem because of physicality. There's none. So in other words, the standard equations are just simply empirical from what they measure, and they say, oh, we'll come up with mathematics to match that, and
it works.
and it works, and it works.
And if I wouldn't necessarily have to go to my 7.5 digit meter. The one I let you borrow the other day would be good enough for me to design a normal circuit.
Right.
This has to do with physics. What's going on inside? Does the TPM model predict, like over here, predict this V-shaped curve? And does the measurements match it? The answer was yes, it does.
Well, part of it though too is because of the speed, right? You didn't think of that at first.
No. The speed came up before I did. The reason I knew about speed is because of the diode in the transistor. The only way I could explain the IV curve of the diode in the transistor was to include the concept of speed.
Okay, and while we step back, are you going to be talking about this, or
yes?
Okay, I'll let you go.
There. Okay. Now, what I did in the measurements, I measured each resistor with my 7.5 digit multimeter using a 4-wire measurement. I didn't do that 4-wire measurement on the first one, but I did now. I learned a little bit more about that instrument, and it gives you a very accurate, much more accurate measurement value of the resistances. Once I measured it, that I kept those values. I measured the voltage of the voltage applied here and the voltage across each one, and then you calculate the current. Current is always calculated. You never measure, even with a current meter. The meter knows the shunt resistor, it knows the voltage across it, and it calculates the current. Current is not real. But that's how I got the current, because I'm measuring. I want to know what the current here, and here, and it's a calculation. Once I know the precise value of the resistance and I got a good value of voltage, I should be able to get a good value of current. Now, this was the circuit without the speed factor. This is a repeat of equations I've already shown you. These are the numbers I used here, and I did these 18 tests. Blah 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 blah. I did the 18 tests with this and this. This shouldn't be down here. That's for the next one. I only used these two values, not the mass here, for this first test. And I already showed you circuit 1 at 15 volts, where this was this is the predicted one. If you look real close, if I would print out these numbers, this is, as I said, less than this one, because there's a little bit of loss in the S1, but there's a lot of loss in the R1, meaning there's very few G1s entering the S2, and that's why it drops like that. This was predicted. I expected it. High, a little bit less, a lot less. Nothing surprising here. And I'm just showing you the results of the 3.9K. This is 2.2K, and there's the 1K, and they're all the same. But this is the measured values. This is not much of a V-shaped curve, but these are V-shaped. This is a little bit flattened out, but obviously this goes down, then up in many cases in the measured value. This one was wrong. I apparently read it wrong or wrote it down wrong, but it's this doesn't make sense at all in this context. And then this is the measured values. They're all V-shaped. Now I'm in the microamp region. This is because all these milliamps are the same: 5.1, 5.1, 2.05, 06. They're all in this. The milliamp portion is in the same range. We're looking at the 4th, 5th, and 6th digit here being displayed. By the way, the meter does not know which equation I'm expecting. It knows nothing about the equations. This is just, these are the measurements, and I have to assume that these are valid. Got a very accurate meter for the resistances and the voltages. And it doesn't matter which equation you think is right. These are the measurements. So the TPM equations, the predictions are wrong. The measured values are correct, and so I have a problem. Quiet?
No, you had a question actually. Catherine, who's following us, she must know somewhat about electrical engineering. Says, so what causes the V?
Oh, okay, okay.
Oh, you. That's kind of the big. Hey, it means someone's following you. And also, I thought it was very interesting. One of the things my father and I've talked about a lot is that one of the problems with models in general is their predictions aren't really talked too much about. Their applications sometimes aren't really talked about too much. Sort of generic kind of things like you can travel speed or faster than the speed of light. But one of the things about the particle model, which requires every force in the universe to be a moving mass hitting another moving mass, what I call a Turing machine, a Newtonian Turing machine, and you got to find out and hack the universe that way, is that we have to have an explanation for this in a physical sense. And so when we are looking at everything, we're saying what biggest question I had was if we use TPM for the particle model on electronic circuits, give it to my father, who's been an electrical engineer all his life, who's been very successful at using empirical equations, using all mainstream has handed him in equations. What would happen? Would it make him look at things differently? And then, after even more than that, would it make predictions that we would not have expected? And one of the things I was saying is that couple things. Electrical engineers in this group, having hung around with people who are outside mainstream physics since the early 1990s in the NPA, Electric Universe, Tesla Tech, the CNPS, the thing that I've noticed is electrical engineers are the most cantankerous, but always the ones who are always questioning things most, throwing the hard questions at people's models constantly. And I always made a joke. I said if everybody had the engineering attitude of an electrical engineer, we would be much better off, because they'll throw questions at you, and they're really the biggest judges. So when my father took this and started applying it to it, I thought this was going to be a huge acid test. And I think it's gone way beyond our wildest imagination about what it took my dad, a 40-year veteran in electrical engineering at high, research, doing digital, design with circuits, to completely rethink about what's going on in electronics, and not only that, make predictions about things that we didn't even know were there. I mean, that's, to me, is, and if you look at all the technologies that humankind has come up with that has made the biggest difference in human history, in my opinion, is electrical engineering. That is electronics, the computer. That has made the biggest difference in mankind, in my opinion. And yet we have zero physicality for any of it. None. And to see my father go through this and then get to a model, make predictions, and struggle with this and have eureka moments, that's quite amazing. And one of the things is that maybe in his second book, which is, Catherine, which is the Physicality electronic circuits, we're thinking of all the electrical engineers out there. They're going to see this, perhaps. They'll read about it. They go, wow, this is interesting. They'll measure it. Then they'll go, why did we have these predictions? They'll look at the particle model. And like you can say, this is great. I'm not sold on TPM, but the experiments rock. That's what she said down here, Dad. This is great.
Yeah.
And so I think it's been really, really amazing to see this journey that you've gone on. So, okay, I'm out.
All right, Catherine. Okay, I heard your question, and I went backwards to this chart. And it's not the particle model. It's not hard to explain why it's the current's higher here and lower there. But when you get to this point, and if there's fewer if this is less voltage, the reason it's less voltage is because it's losing fewer G1s. It's losing fewer G1s than the S1, which means it's passing more through. So if it's passing more through, then this has a chance to be higher. Kind of a simple answer for what causes the V-shaped curve. But here's the real reason. When I did the diode and transistor a couple years ago, I realized that the speed of the G1 through the device could have a way to explain the diode and the transistor. Now, I'm using this because this is the first time when I did this. This was probably back in 2015 or 16 when I did my first drawing of the G2 gravity around a magnet. And what happens is here you have a lot of what I call G2 mass right here in this part, which is part because of the magnet and part because there's G1 particles flowing through there. That's all part of the G2 mass. So there's a large mass here. You got G2 particles coming through here that pass through, and some are hit, and you get a reduction such that there's a net force here, and you end up with a very strong force at either end. There's forces all the way around, and they're also strong. But if you take a look at what this is doing, if this is a G1 particle coming in, and there's a force, a gravitational force pushing on it, just like pushing a G1 pushing on an apple, this is going to accelerate and go faster and faster and faster till you get here, which I'm indicating this is the geometric center of mass, where this force, this direction, balances this force in that direction. So there's no net force at this point, but it accelerates until it gets to here, and now it's at high speed. And now as it goes on further, this force slows it down. So what you really have is that when the F2 force around a component, whether it's a resistor or a magnet, or whether it's a prism, as light enters the prism, it speeds up, reaches a maximum, and then it starts slowing down. But what happens is that if I increase the number of G1s in a circuit, if I go from 5 volts on my circuit to 10 volts, I'm going to have almost double the number of G1s. That increases the mass, increases the force, and causes the G1s to go even faster at 10 and faster at 15. And when they go faster through here, they miss more. And that's particularly true in a resistor. This is a principle, one of the this is a third principle in my book I'm reading now. As a particle enters a larger object, it speeds up, and as it leaves, it slows down. Result, a fast particle will pass through more easily. A slow particle is more likely to hit the object and scatter. So this affects the interaction factor, the speed, it affects it. That's why I showed you this earlier. That's why I added a speed factor in here. Now I got to figure out how do I make an equation for that. Well, this is what I did. The speed factor is based on the G2 mass of the resistor. There is no standard for G2 mass. There is a standard for G1 mass. It's the kilogram. But there is no standard for G2 mass. So I decided, because I have these G1 particles going through the circuit, which in this case is labeled B1, that I'm going to use the G1 particle as 1 unit of G2 mass. So now the G2 mass of resistor 1, which I make this label, mass, G2 mass of resistor, is the sum of all the G1 particles and N1 particles in the resistor. Okay, and it will also eventually include the ones going through. To get the number, I got a speed factor that reduces the number lost. If there's none going through the circuit, this is 0. The reduction factor is 1. There is no reduction. But as you get more and more G1s going through it, this factor goes from, and I got numbers, I should print this out somewhere, but I get numbers from 99% to even down to 80% reduction. And reduces the number loss, increases the number passing through. That's what causes the V-shaped. And this is the same test, only this time I made an estimate of M2R1 of almost 8 billion, and this is almost 8 million G1 units. My estimate, my number. What's remarkable is all of these, in a sense, are my estimates and numbers. Although this was calculated. This is the only one calculated. And this is what I get when I compare the measured value to the predicted. Measured is in blue. The predicted value using those equations, I got the V-shaped curve here and here and here. Oh, that didn't work out so well. So I'm saying maybe these two are wrong, maybe these are right. You can judge for yourself. I'm saying 4 out of 6 are matched. Here I'm saying 5 out of 6. Remember, this is the one that I'm pretty sure this measured value is wrong. So I'm saying, yeah, that's wrong. But I got a V-shaped here on the rest of them. And for the 1K resistor, I got them all V-shaped, although this is quite a bit off. But look at this one. Look at that match. Absolutely amazing.
Hey, this is the first time we've been accused of this. I mean, accused, and this is this person says, I was expecting more mechanistic explanation of the resistor and batteries than the math after. So, but in reality, I guess what he's saying is, well, when you're describing, for instance, the resistor or the battery, what is it mechanically? And we've talked about that, right?
Well, it's in our book, but I just don't have it in today's presentation.
Yeah, I know. Yeah, the thing is, yeah, if you buy the book, in fact, the people, if you want, you can get it for $3 as the. But if you want to get to the book directly, go to tpm.dhilster.com, and that'll get you to the book. And we talk a bunch about the physicality. There's just so much to talk about. It's really hard to get it in. But for the question with the battery, is basically the battery is orbiting G1 particles.
Let me, Dave.
Yeah, go ahead. Yeah, absolutely.
What we say in the book is that when the electrode and the electrolyte, I'm kind of using a wet cell battery as my starting point. You have an electrode, copper electrode, and a copper sulfate electrolyte. And what you have is vibrating atoms in both cases. The vibrating atoms, when I say that it releases G1, is because they're smashing each other, knocking the G1s out of orbit. That's the mechanism that I didn't talk about. But chemical reactions are mechanical vibrations, and that's how the G1 gets released. The G1 orbital released, and then the G2 gravity pushes it out to negative, and then we're going around the circuit. So it is a mechanical process. A balloon. When you rub a balloon on your hair and you pick up electrons in the balloon, that's a mechanical process. It's not chemical. We don't consider it chemical, but that rubbing is mechanical. Lightning, when you build up electrons in a cloud of lightning, the thermals going up and down, they're stripping electrons off of the water molecules and accumulating them in the clouds, creating imbalances that eventually creates lightning. That's mechanical. That rubbing, so even it ends up being mechanical. And there's reasonably easy examples. A Van de Graaff generator, literally, you turn and spin a wheel against one type of material against another, mechanical, and you create this huge charge in the Van de Graaff generator. Mechanical.
Okay, I have another question inside the private. Did you repeat experiment many times for a single
No, I didn't repeat. I mean, I consider the 15 different circuits a repeat, even though it's not the same values, I suppose. No, to literally answer your question, I could go back and because I have the components, I could put it together. I could use another 9-volt battery for the first one and do it that way and try to duplicate. No, I have not done that.
Yeah, I guess part of it's like it's so amazing to even have a model point in this direction, to actually have a physical mechanical explanation in the circuits, and even come close to it at all for the first time with what instruments we have. To me, it's quite amazing. I mean, I don't see, again, I'm this is general support for it. It's not like the finding the one thing, or we're measuring it wrong, so it's all going to be wrong. I think you have to sort of look at the big picture of the model, which is describing everything again as mechanical forces. That, like that one person said, hey, how do you explain these mechanically, and how's it doing? It's doing pretty well. It's describing. I mean, I think part of it is that, right? We're describing how rainbows are made with the same thing we're just talking about in electronic circuits. I mean, to me, it's the big picture. Are our hacks wrong? Are Dad and I's explanations using this model for the first time, someone using this model, going to hold up over time? Maybe not. So, but to me, it's really the overall explanatory power of everything. There's no magic like charge. We have a person asking, saying that, well, in my model, here is a positive and negative. To me, cannot smash into one another. Well, my question to you is, what's the magic between positive and negative? Do you draw it on the little particle and another one on the other particle? What the heck is that? The thing that's bothered me about all my life when in physics is, why in the heck doesn't someone tell me why a positive and negative don't go together? Saying it and just saying that phrase, that's what people say, but there's no explanation. It's magic, and that's what it is. Okay. All right.
I can finish this off here real quick as a summary. My first experiment, I claim that the first one is the only one wrong, that even these measurements, which appeared to be wrong in the first place, were actually right. 93% on the large, 86% on the small, 2 of them wrong. And then finally, the last one, which was which was result I got was 83% match. It's not 100%, but you can imagine that you saw my lab. It's not a white coat lab with a where the climate is controlled, the particle dust are get rid of the particles in the room and all that. This is not a clean room. So I'm quite pleased with the results, and I look forward to. I'm hoping like in a month from now, because it takes me time to get ready to present it. I'd like to continue the discussion of the electronics, where the TPM model has an explanation for the parallel resistors. That's in the book. The IV curves of the diode and transistor in the book. However, I'm not happy with the actual explanation. It isn't as good as it could be, and I hope to cover that in a month or so when I give this type of presentation. That's it.
Well, no, thank you so much. It's great presentation. We have people in the green room. If they want to come up, they can. Let me get this off here. Let me get to some of the people in the chat here. Dennis Allen, who we know from our group. Hello, Dennis. Ron Hatch has shown that gravitational inertial masses differ in general. Can you get this result with your model?
He shows they're different?
Yeah, gravitational and inertial masses.
No, actually, our model says they're identical. My first book, which we don't talk about, which is not in publication anymore, Gravity is Not Free, I discussed that pretty well. The fact is that without giving a big explanation, the G1 particle field that surrounds an object in outer space, as that object moves through the G1 particle, it causes a drag. Okay, but other than the drag, that G1 particle field has a sustaining force pushing it, retarding it, keeping it up and down, left and right in a straight line. The particle without the G1 particle field would move continuously, and I wouldn't have this explanation, but since we have the G1 particle field, except for the drag, G1 particle field keeps that object moving in a straight line and at constant velocity except for drag. Because it's the G1 particle doing it, in that case in open space, it's also the G1 particle that is causing the net pressure on me, pushing me down here on the Earth. That type of gravity is gravitational mass, but it's caused by the G1 by the same interactions as the one in space. So if it's the same particle, the same object, but it's in a different place, the masses must be identical because they're not going to interact differently. G1 is always going to act with an apple out in space the same way it acts as an apple as it's falling on the surface of the Earth. So if the interaction is the same, I say, quote, they're identical. Not only just equivalent. Einstein said equivalent. I'm saying identical.
Right. And I think part of it too, again, we get always back to the same question. There is no mechanical force. There's no mechanical explanation. So when people talk about these things, they're talking about it without a model. And so how are you supposed to judge that kind of
and what
statement?
I just gave was a model.
Yeah, exactly. Okay.
Using the TPM, I gave the model.
Well, anyways, there's some people down here I wanted to show you, Dad. Mark Bender said enjoyed. Frank Fernandez says thanks, great idea. And here's one I can talk about a little too. So, last question: what separates TPM circuit from ether flow? Well, basically, the problem with ether, and there are two people who have been trying. Well, three people who've been trying to do it. 2.5, I would say. Those people are Ionel Dinu, who's working on it right now. He's a Romanian scientist. We use his concept. I call it the Dinu effect, meaning orbiting particles, flows that meet in the same direction are constructive, and the ones that hit each other are destructive, and that is what causes what we call magnetic attraction and repulsion, not very different from gravity. And the other person who is working on that or talked about it, and actually was some inspiration for our model for electricity, was Glenn Borkert, who said, well, electricity are just ether waves trapped inside a wire. That is the big thing. That's the problem. How do you trap ether waves in a wire? I mean, because waves of ether can go through a wall. I mean, radio waves can go through walls. So how does that work? Well, Ionel Dinu, you can look him up. Ionel space Dinu, great scientist. Very responsible for really giving us the mechanical model for magnetism. What he has had to do to get ether models to work for electricity is he literally says there's a new element which no one's ever seen before called electrogen. Now who else worked with Ionel Dinu was Laurie Gardy. Laurie Gardy set out to use an ether model to describe curiously, after we talked about these four: gravity, electricity, light, and magnetism. And that was about 1.5 years ago. And it just sort of disappeared because it's really hard. There's really big problems. I'll give you some problems with the ether. The ether, again, to keep it inside the wire, you have to postulate a new whole element in the periodic table called electrogen, and that I have a model, now I've got to invent something to keep it going. It's like special relativity. You have a special relativity model, you have decay, that is radioactivity. What you measure, it's perfectly logical, but if you apply special relativity to decay, you got less energy than you expect, so you invent something. Dark matter you invent the neutrino. You invent these things because your model can't handle it. So And the other big problem with I even asked Yonel Deleu a couple months ago. I said, you are the one who came up with the spiraling ether as magnetic force, right? Magnetic fields. Well, light is supposed to be propagating through that. If ether is the medium of which light goes through, and you have a magnetic field being ether in going around, how come is it that magnetic fields don't bend light? So the whole thing about ether models for electricity, number one, very few people are working on them. I think the only person even trying it is Yonel Deleu. So you can look him up. He's had to invent another, and to me, it's like Occam's razor. If you've got an idea and you've got to invent a particle because, unless you have some clue. For instance, we have a G2 particle. Oh, you have, well, look at Coulomb's law. It looks exactly like a gravitic equation from Newton. So we do have at least some clue that's there, whereas keeping magnetic fields in wires is really hard.
Hey, Dave. Bob Gray, I've been going through the questions. Earlier, Bob Gray had a question about
Sure.
G1s in the circuit wires, what keeps them there. And actually, that when I describe how parallel resistors work, you'll see that G2 gravity is the force that controls the direction of the G1 particles when they reach a junction. And they also, because of that force, like I showed on the magnet, where you had two strong forces on either end, where you got in a wire you got two strong forces this way, and at the other wire you got it this way. It's slowing down, and this one slows it down, this one pushes it up, and it helps make it turn the corner. It
is a great question, Bob. I asked the same question, and we pondered that for a while, didn't we? I mean, why is it that? I mean, you have that's true. My dad says it, and my dad says, well, this is why, and he and I don't believe each other. Because we will not confirm, and that's the way people should be, folks. Don't believe us. Look at the particle model, decide for yourself. So I would tell him one thing, he goes, no, and then he'd come back to me, and I would tell him something, he goes, no, but G2 particle, I don't care about that. And then he comes back to me 3 months, 4 months later, and says, oh, there's going to be a G2 particle. But I was looking at something like this. You've got a wire, coming into another wire, and it goes both directions. Why doesn't it just go flowing out on this junction, right here? Why doesn't it just keep going? Well, there are forces. The forces, you can imagine, these are like big things in the universe. They have gravitational force, and the gravitational forces on something like this in this direction is much greater than when they're there.
But the parallel resistor not only explains why the G1s decide to go which way they go, but then when you apply that to a large circuit, coming out of the battery, you go to a large circuit, a little bit goes this way, you got to have a lot go this way. How does it know to do that?
Yeah.
The parallel resistor explanation is the start to an answer for that.
Right, yeah. And again, folks, this is why we call our book, Universe Hack 3. Because we have more or less a Turing machine with the four movements of particles in the universe. So that's what we have, and so we have to hack the universe with those things. That is, my dad and I have to take that model with the four classifications. Random direction for gravity, looping for magnetism, just flowing for electricity, and waves of particles flowing together for light. You got to take those four and somehow hack the universe, explain the universe with that at the different levels, because you need all the different levels. All those four occur at all levels. And we are hacking the best we can. We've done pretty well. We think we have a pretty good answer for rainbows. There's the diffraction, where you have a pinhole where light goes through it, and you can see the scene on the back, right? And it flips. Dad and I don't have a great hack for that yet, right?
We're not agreeing yet.
Yeah. Oh. Okay. Well, maybe Dad has one then.
Well, we both sat there and talked about, you had your concept, I had mine, and nobody walked away happy.
Right, that's true. And I don't think we're there yet. But again, so what we have given a system called the particle model, the Turing machine for the universe, made of how do you say, Newtonian mechanics. How we hack the universe with it, we're the first ones to try. Is it right? We don't know. So, yeah, maybe it could be wrong.
I made a comment in the book when we give you impressions. You work with it like we have, and you get to thinking, wow, this is great, this is great. And you ask yourself, could this really be real? Could this be the real world? And then I get a bit of caution by saying that we don't have direct evidence for any of it. I have no meter that counts the G1s as they go into a resistor and as they come out, so I know how many left. There's no meter that gives me direct evidence of what's going on for none of it. So without direct evidence, there is no proof.
Yeah.
But the experiments are indirect evidence. I have voltage and current as evidence for the model. The model predicts a certain behavior that way, and it verifies it. But I got voltage and current. I don't have G1 flow. We have indirect evidence, which is supporting evidence. Now, if you get enough supporting evidence, if it builds up, just like relativity, they claim they have supporting evidence. You get enough of it, you start believing it's real. That can happen here too, but there is no proof for this. So, if you're hoping to say, hey, well, I'll jump on this bandwagon because we can prove this and we'll prove that. Worked 6 years on this, and I don't have one bit of direct evidence for this model.
But I will tell you, if I were to I'm going to give you my honest opinion, even if it wasn't my model. One of the things that we never answer for the public or people, or I have never had an answer, is what is this stuff? We talk about for instance, we have a person here, quasars, electromagnetism. Well, what is electromagnetism? What is it? We talk about it, we write equations for it, but if a person on the street who doesn't want to know all the technical details or anything, they just want to know what it is. One of the things we found with our model, especially on our day we had to give talks to our friends and family who care less about this stuff, is they were like so amazed because someone finally walked up to them, looked in their face and says, light are particles in groups coming at you, and the frequency that they hit you with, that gives you the frequencies of all the colors and all that stuff. That's what we think it is. Magnetism, what is that? Oh, those are loops. Particles are going around and around, and when those loops are in the same direction, wonderful. That kind of situation attracts. When they hit each other, that's a repulsion. They go, wow, what causes gravity? Of course, many of us know the graviton, but they don't. What's electricity? Oh, it's just these same particles flowing. It's all what we have given the public, right or wrong, is something that it gives a physicality to everything in the universe. Even if we know that a nucleon, if you universe hack 4, if you get the book, we talk about that. I talked about it a little last week, that the Jeff Yee's configuration of putting these nucleons together have equations that make the electrons, the G1 particles, stay in this kind of orbit. Yeah, because of the G2 field, all of that can be explained. It can be hacked, can even be modeled. The thing is, though, is all of the models always have some magic in it. There's magic. If you got the ultimate particle, it's magic. Because what makes that particle? I don't know. Because it's an electron, like in the standard model. It's got a negative on it. Why does it have magic? Charges magic. Fields that have no physical explanation are magic. And that's why we get into all these arguments. So, right or wrong, in my opinion, this is the first model that actually can try to give physicality to everything in a Newtonian sense. And that the new models out there, Borchert's model, Yonel Deneu's model, our model. There's some other people. I think Laurie Gardy was working on a model as well. All of those people agree that things like charge are magic, and we have to explain them without the magic of plus and minus. And so these things are happening. So to me, that what makes us satisfying this work is that we finally can walk up to somebody on the street and say, well, at least according to this model, this is what light is. This is what gravity is. This is what magnetism is. So when somebody sees that, they can in their mind say, oh, this is a magnet, and there's things flowing around it. Oh, atoms stay together because the same G1s are going around nucleons, and they cause flows, and those flows either conflict or they react better together, and in their mind, they can create stuff. So again, right or wrong, it is the first attempt, in my opinion, to see a model that everybody says, no, this works for the whole universe. I've heard it. But it's all symbolic. It's arbitrary systems with arbitrary attributes with no physicality behind it. And then you get people literally coming up to me and my friends at my work who are pretty bright saying, of course tensor equations are real physical things. I'm thinking, So anyways, I want to thank my dad for his presentation. Dad, thank you so much. I think it's really remarkable the simple experiments that anybody can do as long as they have a 7.5 volt
By the way,
mirror.
You could rent it for I rented it for $150 a month. Rent you a meter. You can duplicate these experiments very easily in your own room.
Yeah. So, okay. Well, thank you so much, Dad. We're going to be getting out because we are time, but I really appreciate it. And let's all go out. And again, next week, be sure to tune in. We got Eric Reeder coming in and talking about the history of quantum mechanics. And also, he's a person who has some ideas beyond quantum mechanics where it goes wrong, but he's going to talk about the whole history of it. And of course, thank you everybody for your support, and we're going to head on out as normal. Remember, stay critical, stay thinking. I'm Dave D. Hilster. I'm your science therapist trying to get you to the promised land of becoming a critical thinker. Ciao for now, folks. Till next week.